of them floating around. And you can tell because they get to wear a colored flag instead of the subdued flag. And then they got their colorful little missile Star Trek looking thing underneath that.
Programmers in the Space Force a bit.
Alrighty, so I hope everyone can see my screen now. I've got last night's big O problems up on the board. I figure we can just walk through these one by one. Could pick one person at random, or someone can volunteer themselves to just talk through their thought process. What do you think the complexity of these algorithms is and why? So start out simple. Who wants to do the first one? I'd be hoping that you'd be eager to do the easy ones so I don't call on you for the harder ones. That's the strategy here.
Would it be O of n?
Why would it be O of n?
Because it looks like it can only take in, for value, it'll just be one number. It's not a list or anything like that. And then the array, I mean, obviously it's an array, so it's proportional to the size of the array.
Yep. So again, when we're talking about complexity analysis, we're always concerned about the input growing. So there needs to be some kind of an array or other data structure that we're processing that could potentially be larger in future calls. So that's right, value is probably just a single item. So that's not going to increase. All we're concerned about here is array, which, based on this code snippet, looks like it's supposed to be just a plain one-dimensional array. We just do a single loop straight through it. There's an if check inside of it, but that doesn't like exponentially increase our complexity. That's just one check in our loop. So yeah, O of n looks correct to me. I don't know if anyone has any dissenting opinions. No, yeah, this one's pretty simple. So thanks for that. Thanks for getting the ball rolling, getting us started here. So moving on, getting a little bit harder. How about for this info dump? What's the big O for this problem?
It'll also be O of n. Go ahead.
Okay. I'm not going to say you're wrong. Can you talk me through why? How'd you come to that answer?
For this one, we have two consecutive for loops, so both are in complexity. Since they're not nested, it will reduce down to O of n.
Okay. Why don't we call that O of 2n?
You could, but we were using just the reduced value.
That's right. So when we're calculating the big O complexity, we're not really concerned with small differences in runtime speed. We're looking at the very large differences as the input gets very large. And so in this case, strictly speaking, yeah, doing the for loop twice is going to be twice as slow. It's going to take twice as much time as just doing it once. But at the level of detail we're looking at for a big O analysis, we don't really care. If one algorithm is going to always be twice as slow as another one, they're still the same complexity. It's about if the runtime grows faster than some other algorithm as the input is increasing. So here, the runtime increases linearly for each extra customer we add. So we would still describe this as O of n. Kat, did you have a question?
Yeah, I'm just wondering, so the number of iterations, if you have two loops, if they're doing a different number of iterations, are they still both O of n, or are they not necessarily the same complexity?
I mean, so it depends on why you're doing the number of loops you're doing. If both of those loops are based on the same array, one is, array.length and the other is array.length minus 1, then you have a situation where adding one item to the array increases the number of loops you do and increases the number of checks you do per loop also. So that compounds. Every item that you add increases it by even more than the previous item, where in this situation, adding one item to the customer's array just adds 2 iterations because we're doing 2 individual loops. Does that help?
Not like entirely, but I think it's just hopefully gonna come together eventually. But
Do we
yes,
have
thank
a
you for answering.
follow-up question, maybe?
Not a question, just a comment on it. It's because like in this one, like the time increases linearly with each extra array added. Because an extra element adds 2, 2 extra elements adds 4. So it is like O of 2n, but it's that linear increase in time that causes it to be O of n, right? And not a different O of something else.
Yeah, thanks. I guess, I don't know if anyone's still comfortable with their like middle school algebra, but if you were gonna like graph this, like the simplest possible linear algorithm would just be like y equals x. Something like this, you might graph that as like y equals 2x. So it's increasing twice as fast, but it's still linear. It's still going to be a straight line, just slanted up more slightly. It's when we get into the curved lines that, you know, you're looking at something that either increases faster for each item or increases slower for each item, depending on which way the line curves. Kat?
Oh, sorry, I just didn't put my hand down, but thanks for
Oh.
what you just said. Kind of, I think that made a lot of sense. Thank you.
Okay, cool. It just popped your name up again suddenly, so I thought you re-raised your hand. That's cool. Do we have any other questions about snippet number 2? No? Okay. Snippet number 3, what do we think?
This should be 1. Oh, 1. Oh, 1.
Yep. So given our understanding of how, you know, arrays should work, there's no iteration in here. We should be able to directly access this element by its index. So it doesn't matter how long the rest of the array is, we're always going to access the first item in one operation. So yeah, I think someone's already said it, but since it doesn't depend on n at all, this is just O of 1. Is that clear to everybody? Wish it was easier to see everyone nodding. Cool, so let's talk about snippet number 4. This is where things are getting a little bit trickier.
Is that O of n squared?
Maybe. Why do you think that?
Because there's a for loop. Well, so with the first for loop, that's going to increase by linearly, and then there's a for loop within that for loop, meaning that as this for loop increases, then there's going to be another for like the for loop goes based off of that one. So in my head, I'm thinking like that's gonna like, because it's like a nested for loop, it's gonna make it squared.
Yeah, it squares it. That's exactly right.
Yeah.
So the critical bit here is A, we have a for loop inside of a for loop, but also important is that both of those loops are going over the same array. They're both looping
Yeah,
over the
that too.
input array.
That too.
So imagine if the input array was 2 items long, this is a 2 iteration loop. And for each iteration, we're doing 2 more iterations. So it gets us 4 iterations. If this was a 3 length array, we would be doing 3 loops in our outer loop. And then for each of those, 3 more iterations in our inner loop. So 3 times 3 is 9. So it's just the length of the array squared is the total number of iterations we have to do for this loop inside of a loop. So yeah, we would describe that as O of n squared. Everybody else got the same answer? Cool. All right, so now we're getting onto slightly trickier problems. Not harder, but trying to just make sure you know what you know. So what do we think is the algorithmic complexity of snippet number 5?
This as a O of 1 because even though there's a nested for loop, words and endings are not changing.
Mm-hmm. That's
Like
right.
it doesn't change. Yeah.
So yeah, the critical observation here is that we're not running this code inside of a function. It doesn't accept any arbitrary input, but rather we're looping over these two hard-coded arrays. You know, this one's got 3 items, this one's got 3 items. You know, there's not a lot of context here, so it's hard to say for sure, but it looks like based on this limited example, there's no reason why these arrays would ever become bigger than they are. So this is just always going to be 3 iterations of a loop with 3 iterations of another loop inside of it. So we're iterating 9 times, but this doesn't increase for any reason. So I suppose you could say that this is O of 1 complexity, but I might even say that it's not sensible to analyze this code with big O analysis, because one of the assumptions of big O analysis is that your input is increasing to infinity or some very large number, and this snippet just doesn't actually have any input. It's just processing hard-coded data. So I think I would accept either of those answers. Snippet number 6. What do we think?
Snippet number 6 will not return anything.
It's going to return error, array not defined. Unless if numbers is meant to be the array. This number is meant to be array.
So I guess they show us the test data and they show us the function, but they never actually show us, we never actually see them calling the function. So
Yeah.
maybe there's some missing context. So let's imagine. A second. Oh, what am I doing? This is definitely Python. Okay, so let's imagine that this function is actually being called and the numbers array is being passed in. So I think people were noticing that the variable names were different, but you know, you can't actually tell if it's mismatched if you don't see how it's called. So the variable in the outer scope
Now-
is called numbers, we're passing into print array. Inside of print array, it's just called array. So now, what do we think is the complexity of this algorithm?
Now it's O of n. And I think it's O of n because every time you increase numbers by 1, it's going to increase the complexity by 1 because it's going to have to loop through it one more time, making it increase linearly.
Yep. This is a pretty straightforward, just looping straight through. Honestly, a little simpler than I would expected for snippet number 6. Could have put that maybe earlier, but just want to get you to second guess yourself and overthink the problems. So for snippet number 7, what do we think is the complexity of this algorithm?
I thought maybe O of n log n. And I said that because the first is just a for loop, so I thought that was constant. And then the while loop, I kind of thought maybe it was like a divide and conquer kind of thing. So that made me think log, but I'm not sure.
Okay. Some good ideas there. A lot of times when you do a divide and conquer kind of strategy for these algorithms, you get something better than linear time. I'm not sure if that's what we're getting here though. Does anyone else have any thoughts? Any guesses or hypotheses?
I thought it was just the O squared or O n squared
Mhm.
because of the 2 loops.
Yep. we do have two loops. Are they both looping over the length of the input array?
No, one looks like it's gonna keep getting shorter.
Okay. So yeah, because got for I in range from 1 to the length of the array. So this first for loop, this is definitely looping over the full length of the array. And then we have this other loop, while j is greater than or equal to 0. So what's that loop about? Like, how big is that? Is that also the length of the array for this j loop?
Is it half every single loop? Looks like maybe, because j equals I minus 1, so it's subtracting.
Mm-hmm. So it's always going to be smaller, it looks like. This j loop is going to be smaller than the I loop. And especially because we also have this other condition that can stop us from looping if key is less than ARRJ. So for sure, this inner loop is smaller than the outer loop. So it's not like fully n squared. But remember, in big O analysis, we often ignore a lot of the smaller factors. So I'm not actually sure if this is faster enough to make it not O of n squared. Andrew, did you raise your hand?
Yeah, so while it is a smaller loop, we still have to go through every value of I, which is every value of j, and we have to look at it in like worst case scenario.
Mm-hmm.
So we are going through the entire, we're really just going through the entire array again. So I feel it is like O of n squared.
Yeah, that's a really good point. When we're talking about complexity analysis, we're generally very pessimistic. We're mostly focused on the worst case scenario. Because honestly, like we don't care, if you're processing 1,000 items in an array, you don't care if one of them happens really quickly. You just want to make sure that none of them are unacceptably slow. That's usually how the prioritization works. So yeah, we're concerned about the worst case scenario here. So, we do have this opportunity here to short circuit this loop. This key less than ARJ could become false. But in the worst case scenario, if the thing that we're looking for is just in the last place we look in the array, we'll end up doing almost a full, nested loop of our same array. So let me just double check this. This actually just says here, this is insertion sort. I'm just going to check this handy dandy graphic that Ankur showed you the other day. So yeah, here it tells you definitively insertion sort has O of n squared as its worst case complexity. So it sounds like our analysis was correct. Does that make sense to everybody? Is anyone still kind of confused about why this is still n squared, even though it's slightly faster than that, or maybe doesn't look like that? No? Okay, cool. Everyone gets it. Amazing. All right, so last but not least, our most challenging snippet. What is the complexity for snippet number 8?
I think it's O of n squared just from looking at it, because I see that it's a nested for loop, or maybe because it's doing I plus 1, so maybe O of log or n log n. But I think I would like, just from looking at it without, it does look like O of n squared, because it's a for loop and then a nested for loop.
Mm-hmm. Yeah, that would be my analysis of this question. Doesn't look like there's anything else inside of here that would change it. We're just doing a loop for I in the range of my list, and another loop for j in the range of my list. Starting at I plus 1, but I don't think that's enough to make it faster than n squared.
Okay.
I have to agree. It looks like almost close to a bubble sort. which would be O of n squared.
Yeah, that's what I
Actually,
would
it is a
say.
bubble sort.
And bubble sort, is that on our list here? Yeah, bubble sort looks like it's got the same time of complexity as insertion sort. Cool. Ankur, do you have any thoughts, any wisdom to add about this last snippet for big O complexity analysis? I don't know if there's any nuances I missed here.
No, I need to look at it. Sorry.
No worries. Yeah, this big O kind of complexity analysis is not obvious at first glance. That's why this was a homework problem. Oh yeah, because that if statement doesn't even return. It won't short circuit the loop.
Yeah, I mean, it looks like O of n to me.
Not O of n squared.
No, because it's just doing that for loop, and then it's just trying to assign min index. Like we're not. I don't think we're doubling up on the inner loop.
You wouldn't say this is just a second loop over a similar range. Lend my
Oh,
list.
sorry, I didn't see the outer loop. Yeah, sorry, no, n squared would make sense to me. Sorry, I thought that was a function, but
Yeah.
n squared would be my analysis there.
Yeah, I guess this snippet is written with a slightly different syntax from some of the other ones because the other ones all start with a function definition. So this one doesn't. I guess it's easy to misread. Cool. Thanks, Ankur. All right, so it looks like all these were either O of n, O of 1, or O of n squared. So looking at our cheat sheet here, we didn't see all the complexities. Excuse me. But honestly, we saw, I think, the most common ones at least.
Yeah, could you go over a O of n log n? Because honestly, I don't know what that would like. I think since the problems mostly went through that, I feel like I don't really understand O of n log n as well as I understand O of n squared or O of n.
So I would agree with that just because I understand exponents better than I understand logarithms. But so for one example, binary search is, wait, did you say n log n or log n?
Either one. I also mostly understand like the exponent ones.
So let me think. So binary search would be a good example of a log n operation because you can do that faster than linear time. So I guess linear time is a good kind of baseline comparison. So, that's your O of n here, that's linear time.
Okay.
So, you can intuit that pretty well. Like every time I add one item, it's going to add, a certain amount of time to the runtime. When I add another item, it's going to add the same amount of extra time. So with an algorithm that performs better than linear time, so log n, that means every successive item that you add to the input increases the runtime by less and less time. So, maybe you have a log n algorithm that takes 10 seconds, or well, I don't know, let's say it's taking 10 seconds to process 10 items. You add an 11th item, and then that adds, 0.9 seconds. You add a 12th item, and that takes an extra 0.8 seconds. 13th item takes an extra 0.7 seconds. So it does get slower as you add more items, but each successive item that you add to the array makes it slower and slower by a smaller and smaller amount. So like the more items you have in the array, the less you notice adding a single item to it. Does that make sense?
Yeah, that makes sense.
Okay, that's kind of how I think about log n algorithms. And then n log n, I guess, is kind of a similar idea. Like if you can recognize intuitively what a linear algorithm looks like, but you know that it's not as bad as a quadratic algorithm. Because like most people can recognize square numbers, if you have a 3-length array and it does 9 iterations, you would put in a 4-length array, it does 16 iterations. We all know our square numbers pretty reliably, I think. So it should be a little bit easier maybe to recognize an O of n squared algorithm. So if you can tell that you've written an algorithm that is clearly better than O of n squared, but it's not linear, very good chance that it's n log n. But honestly, I don't think that n log n algorithms or log n algorithms are as common. Those are like kind of more clever algorithms, I think. If you're just trying to solve a problem, get stuff done in the simplest way you can, I think most likely your intuitive solution is going to be either linear, constant, or quadratic. And if it's quadratic, you should maybe try to refactor it so it's not. Does that help kind of put things in perspective a little bit?
Yeah, that helps.
Cool. John, did you have a question?
It's more of a comment, and Andrew Liu or Anker could probably chime in for it. But for the n log n is basically if your inner loop is dividing the number of items rather than subtracting the number of items.
Can you say it again?
If you have a nested loop, but your inner loop is dividing the number of items that are left rather than subtracting the number of items that you have left, then it becomes n log n rather than n squared.
Okay, so like in the binary search algorithm, how we cut the array in half for every iteration.
Correct.
Okay, yeah, that makes sense. That sounds like a pretty good heuristic, I'd say. Just like we kind of look for a loop inside of a loop and say, oh, that might be n squared. I'll take a look at that a little further. Yeah, if you see in an inner loop, you're dividing your input instead of subtracting from it. I think that's a pretty good clue that you might be looking at a log n algorithm. Bao, did I see your hand up?
Yes, just a quick question, Raf. I've been struggling with this one scenario where there's like, instead of 2 nested loops, there's like 3, 4, 5 nested loops. Would that still be the case of like O of n squared, or that'll be like n to the 3rd or to the 4th? How's that work?
Yeah, so if you have a loop inside of a loop inside of a loop, all iterating over the same array, that would be O of n to the 3rd power. Excuse me. I'm not actually sure how you would write that down. Ankur, maybe you could clarify. Would you just condense that to O of n squared if it was actually like O of n to the 3? Because it's still like the same, not like order of magnitude, but like kind of the same rate of change, like the same order of function. You know what I'm saying?
No, I think it'd be a separate classification. So it'd be like, yeah, n cubed algorithm would be a separate line on this chart.
Okay, so not featured here, but it would be kind of here-ish roughly.
So that's not necessarily the case where 2 of n power, because I keep mixing them up for some reason.
Oh yeah, 2 to the n power, that's more like the factorial calculation algorithm, I believe. Yeah, it's a little bit harder to, or wait, no, I'm sorry. N factorial is the factorial algorithm. I'm not sure off the top of my head what would be exponential complexity. But generally, like as a professional, I know how to recognize quadratic complexity and know that anything that it is that bad or worse is unacceptable if I can't control the size of the input. So if I know it's in this red zone anywhere, I'll refactor it.
Okay, thank you.
All right, do we have any other questions on Big O part 1?
Yeah, okay, I'm sorry, can I ask one more?
For sure.
If, so like, let's say one loop, there's a loop inside a loop. One is like, every time you double the size of like your list, it increases it like doubles, but the second loop, let's say it like goes 4 times as much. In big O, we wouldn't recognize a difference between those two. We would just see both of them as linear. Is that right?
I'd say that the difference between the 4 and the 2 doesn't matter. We would call those constant factors. So if you have like an outer loop that loops over an array, and then an inner loop, you're looping over that same array 4 times. So that's worse than just a regular quadratic complexity of just a loop inside of a loop, because you're doing 4 iterations of the loop inside of a loop. But that doesn't change the algorithmic complexity the way we would write it.
So I'm thinking of like the example, I think it was snippet 7. When I like ran it through, I thought that like each time the outer loop was actually just doubling the amount of iterations when we doubled the size, but the inner loop was like on average like 4 times as many. So would those two still be kind of rounded to the same type of complexity, like each one?
Yeah. Yeah, those would be the same. All right, any other questions? I kind of want to go on to Big O Part 2, just review a couple of the past exercises at student's choice. But this might be a good time for a break. What do people think? Do we want to continue some exercise review, take a break right now, or a third thing?
I guess we can take a break.
Okay. Well, that's what I wanted to do. So if nobody said anything, that's what was going to happen. So let's come back. We'll make this a little bit quicker. 7 minutes, come back at 10:50, and then we'll pick some random volunteers for Big O notation part 2. Hello, welcome back, class. So before we dive into some more Big O analysis, I just want to acknowledge someone said in the chat, the recursive Fibonacci algorithm is a good example of an O2 to the n algorithm. So I was struggling to come up with a good example just a second ago. But we were wondering, what kind of an algorithm actually increases this quickly? So the recursive solution to the Fibonacci sequence gets this slow that fast. That's why we can only demo it with inputs of like less than 20 or 15, as opposed to the iterative solution as this nice non-curved line. So that's a really good example of, when algorithmic optimizations make a big difference in performance. All right, so the Big O challenge number 2 was pretty open-ended. Ask you to look at any or all of your previous exercises. Is there any exercise in particular that we want to look at, or does anyone want to just volunteer to talk us through one of the exercises that they want to analyze? Don't everyone jump at once. I guess, was there any particular exercise that people got stumped on that you just couldn't figure out what the complexity of it was? Not so much. I guess everyone just did great on Big O number 2. Figure out the complexity for all of our past assignments. Does kind of seem like a lot.
I'm not gonna lie, I spent more time in the 4th module of the school challenge than I did in Big O last night, so.
That was probably a good use of your
I
time.
think that might be an issue.
Pardon?
I was just going to say, I think that might be the issue, is that people may have done the first one and then dedicated time to understanding some of the problems previous before moving on to the second one.
Okay.
I,
So yeah,
I mean, I have a question kind of about the whole bubble sort. So for the bubble sort, so I guess I solved it first, and then I also kind of went back and tried to find like a way where it's shortened, like even more dense than it already was. Like right now, I just have basically like 2 for loops. And after I solved that, obviously I went in Google and I was like, you know what? Like, I want to see what's the best possible answer. And I saw one where he got like a catch where it would avoid looping the whole thing. So basically, like I was just saying, like, what would you be like your goddamn best performing bubble sort solution? Because right now the way I have it is like basically generic. And the way that the guy showed it on the YouTube video was like he had like a catch where it would, if it's already sorted, it's not going to go past a certain number and just restart the loop. And he went super crazy with it. And I was just going to see like what would be your, as a professional, like goddamn perfect solution for the bubble sort.
I mean, honestly, as a professional, I would not write a sorting algorithm. Maybe if I were a computer scientist, I'd have a different answer for you. But like from where I'm sitting, I think it's interesting to know how to do some of these sorting algorithms by hand. But the truth is that like very smart people have been studying for years and years about how to optimize these sorting algorithms. Like there are some people who are not engineers, they're not application developers. All they do is just like sit in universities and try to think of slightly faster ways to sort arrays. And I really appreciate those people for the work they do, because you know, those sorting algorithms are now part of all the programming languages we use, and so I can leverage them. So like I've shown you before how to sort things in JavaScript, and under the hood, I hope that that's using some like really elegant sorting algorithm. I want to say it's. So I was reading the other day, Python uses timsort for its internal sorting algorithm, which you can see here, best case is just amazing. And then the average and worst case is still very good. It's not n squared in any situation. I don't know exactly what sorting algorithm JavaScript uses under the hood, but I'm hoping it's something that's similarly fast to timsort. So I appreciate people, you know, doing the work to make these algorithms available to me in my programming languages. But for me as an application developer, I need to just describe the programming logic, the business logic of what goes before what in the array. And then the lower level algorithm kind of handles the nitty gritty of how many comparisons are actually necessary to get it sorted. Because if I was doing it manually, I would probably do too many comparisons just for not being the clever sorting algorithm writer that some people are. So yeah, if you saw a solution that I did, it would probably be pretty basic and conventional. I don't have a whole lot of tricks in mind to optimize those kinds of things. Andrew?
I actually wanted to talk about bubble sort too, but
go for it.
Kind of like a question for it. So I did the basic version of it and I did the improved version of it. But my question is this, like, so the improved version only improves it in terms of runtime, because so in the basic version, if you find something to swap, they swap, and then you go all the way straight back to the beginning, and then you go back up through everything. But in the improved one, it swaps, and then it keeps going through, and then it swaps. My question is this, like, even though it's improved, and I tested this, and I just wanted to make sure, to get the final solution, they still both have to do the exact same amount of swaps.
It might be the same amount of swaps. I'd have to look at it a little bit more closely. I mean, can you rephrase your question, I guess?
I'm just wondering if that's like if it's supposed to do the exact amount of swaps, or is it just like the efficiency just like goes up because you're not restarting the chain every time? I was just wondering if like you were familiar with how like the improved one works.
So I don't have a specific answer to your question. I'm not exactly sure how the improved one works compared to the basic version. I will say though that in practice, There are a lot of meaningful differences in performance that are not described by big O notation. 'Cause, you know, in big O, we don't care about the constant factors. We don't care about coefficients. O of n is the same as O of 2n because we're concerned with the input going to infinity. But like practically speaking, you know, if there's a process in your business that takes 10 minutes and you tell your boss you cut it down to 5 minutes, like that's not a speed increase that big O would measure because you just cut it down by half. You didn't, you know, change the growth from like exponential to linear or whatever. But you also like cut a process in half. So it's on like human level that's very meaningful. So I'm sure that there's a lot of room for optimization for these sorting algorithms that doesn't actually change them to a different complexity class, but still like in practical terms, increases their speed and, you know, like it's worthwhile. People would prefer to use those faster algorithms. All right.
Yeah, I was looking at that as well, and it's just basically if you make, you know, an entire pass with the bubble sort and you didn't have to make any swaps, then you know it's already sorted, so you can just stop. But nothing will change the time complexity of bubble sort. So that's what I found.
Yeah. It's a nice challenge because it's easy enough to write by hand, but yeah, you can see from this chart that there are other more performant sorting algorithms. All right, so it's almost 11 now, so I think this is probably a good time to jump into some actual lecture content. We're going to talk about, not that. Let's gonna make a new folder for this. All right, so today we are learning about data structures. I know we've already been talking about these a bit. You've learned about a few of them, but today we will be formally introduced. So let's start with the definition before we get too deep into things. So in computer science, data structure is a data organization, management, and storage format that enables efficient access and modification. So another way that we can say this, which I think is kind of a more plain English phrasing, a data structure is a collection of values, the relationships between them, and the functions or operations that can be performed on them. So for example, we might say an array is a data structure or a list is a data structure. It's a one-dimensional list of values. That's your collection of values. The relationship between them is that they're all sequential. Everything in an array has an index. And then there are functions that let you operate on array items like push and pop or index of, remove, etc. So these three things together, the data, how they connect to each other, and then what you can do to it, this is a data structure, generally speaking. So I know for one of my previous lectures, there was a question, why are we doing this? Why does this matter? What's the point? And, you know, I like to kind of tell a story and then build up to my big conclusion at the end. But I guess some of you just can't handle the suspense. So I'm just going to give that to you up front. Why does this matter? And or why is there more than one data structure? I think is another way to phrase this question. if data structures are so fast and performant, like why don't we just choose the best one and use that for everything? So here is the simplest, most concise way that I would answer, why do we care about data structures? Why are there multiples of them? So different data structures can perform different operations at different speeds. So as you're designing your application, depending on which operations you need to perform the most often, you might choose a data structure that prioritizes those operations over others. So reviewing back to this big O cheat sheet here, we got this table of common data structures operations. I think this is a great table. This is kind of just one image that sort of sums up like, why do I care about data structures? And so I can look at this and think like, okay, am I more concerned about the average case, making sure that, on average, I'm processing things in a minimal amount of time, or am I most concerned about the worst case, making sure that no one user has a particularly bad experience or something like that? And then similarly, am I more concerned about accessing elements directly or searching through the data structure, or am I more concerned about insertion or deletion? This is, I think, a pretty common design consideration that's going to come up in your career as you're, choosing what tools you want to build things. Either you can optimize for inserting data into a data structure, and that makes it a little bit harder to get it out afterwards and process it. Or you can optimize for reading from a data structure, but that'll make it a little bit slower to add new data to it. So there isn't like a right or wrong answer here. This is, you have to make a hard decision about trade-offs in your applications. This is why engineers get paid the big bucks. We aren't just code monkeys who, know how to type out code and make the application run, but we have to be critical thinkers and decision makers that can choose proper data structures depending on the anticipated needs of our application. So that's like kind of the big headline message that I'm trying to give you. Choose your data structures depending on what your application needs to do. It might be kind of hard to like think about that at this point because a lot of the programming we've had you do is like solving challenges and puzzles where we give you the data structure, and then the hard part is you figuring out an algorithm that lets you, achieve the desired result from that data structure. But practically speaking, in your day-to-day job, you or someone at your company got to choose the data structure. So sometimes instead of writing an overly complicated algorithm, you might consider that actually you just started with the wrong data structure and that maybe you should try to get the data in a different format, which is not always possible depending on your company's politics and technologies and partners and whatnot. But it's a good question that you should be asking. Like, am I writing the wrong algorithm or is something else already messed up and we have to go back even further? So before I talk about a whole bunch of like new specific classic data structures, I want to try to do a little thought experiment here, try to drive this point home with some data structures that we already know about. So I'm just going to ask some basic questions to the class here. So let's consider a basic list. I'm going to put a little JavaScript syntax here, a little JavaScript snippet. All right, so we've got an array of letters. So hopefully this is review at this point, but can someone tell me what is the complexity for appending an item to the end of the list?
Oh, one?
Yeah,
O of n for insertion.
getting some different opinions here.
I would say O of one.
Okay, so O of one, folks, why do we think it's O of one?
Because it doesn't, the append doesn't go through the array at all. It just throws whatever you're appending onto the back of the array, and it's not actually looping through the array.
Okay, people think it's O of n, why do you think that?
Unless I misunderstand insertion, insertion should be O of n according to the complexity chart. My guess is because it's going through the whole array and appending at the last index.
So referring to this complexity chart. So it does say, I hear what you're saying. Array insertion says that's O of n. I think there are some assumptions made in this chart though. So there are like more variations of these situations that are not described here. So I believe that what is assumed in this chart is that you are inserting into a specific place in the array. So
Understood.
So let me ask a slightly different question. What if we wanted to insert an element to the first position of the array?
So
What's the-
data one equals element or data zero.
So not even that. So we're not replacing the first element. I guess I should actually put some code up here so you know what I'm talking about. Say data dot unshift, and we'll put a Q in there. So unshift adds an item to the start of the array, and that's going to push everything forward. So A, after we unshift Q, A is going to be the second index, X is going to be the third index, etc. What's the complexity for adding Q to the start of the array?
I would think it's n because you have to go down the list, pushing everything back.
That's right. So adding an item to the start of the array is O of n because you have to update the index for every item after it. So, so that's the worst case for inserting an item. Because, you know, if you insert it to the end of the array, there's no items after it. So that's the best case. That's just O of one. But if you insert it at the start of the array, every other item in the array is after it. So that would be O of n. So if you're just talking about the complexity for insertion and you don't specify where in the array, I guess the most fair way to describe that is that's O of n. But I'm being a little bit more specific here. I'm just talking about the end of the array. So in that case, since you don't have to update all these other guys up here, or even this guy, and you're just changing the length of the array and then adding one new item to the end, that's just going to be O of one.
So should your note for that unshift say start of the array? Because
Yes,
it would be a push for
yes,
the,
it
okay.
should,
All right,
because
I
that's what unshift does. Thank you. So whereas data dot push, put an L there. This adds L to the end of the array. And I think we already heard it. That's going to be O of one because we only make one change, doesn't have to update the rest of the array. We can do this just as fast, no matter how big the array is. So that's great. So what about searching through the list? What's the complexity for searching the list? If we just want to know the index of G, what do you expect is the time complexity to just get the index of G?
Oh, then
O of one.
Okay, we're getting some different opinions here. Why do you think it's O of one?
Because the function of find index of is not changing the array at all. It's just finding the position of G and returning where it is.
But how does it know where G is?
I guess, well, it's looking through it, but it's still not changing the input.
Does it need to change anything?
Yes, from my understanding. Oh, it doesn't.
We're just
Okay,
concerned
someone's saying
with
it
the
doesn't.
number of operations. Sometimes you're just reading, writing is also expensive, but 1,000 reads, that becomes 10,000 reads with 2 items, becomes 100,000 reads with 3 items. Like the
Then it would
reading
be,
gets expensive.
okay. So it's O of N?
Yeah.
Okay,
I can't think of any way that I could implement an index of function without looking through every element of the array. So maybe I should check the source code for JavaScript, but I'm pretty sure that this is O of N. Okay, great. So that's a list. So we're going to get a slightly different example now. Okay, so now we have a sorted array. So, I mean, for one thing, you can just see here that these letters are in alphabetical order, but also I'm telling you that this data structure is a sorted array. It must remain sorted. If we're going to talk about any modifications that we want to make to this array, just make sure it stays sorted afterwards. And just always assume as we're accessing this array that it is sorted. So now, let me ask you again, what is the complexity for adding one item to a sorted list?
Are we assuming that we're sorting the list, or are we? So like, it's gonna be sorted when we're done appending?
One way or another, the list must remain sorted after you add the item.
so that's O of 1 because you're not going through the list, you're just adding to the end of it.
Okay, but we need to make sure that the list remains sorted afterwards.
Okay.
If we add a
sorted.
sorted
Okay, yeah,
item, it
sorted.
sorry, go ahead.
No, it's okay.
I was gonna say, if we add a sorted item, I believe it's log n, or I mean, sorry, n log n.
Why do you say that?
I'm looking for the chart that we were looking at, but to add it sorted, it's like it adds a whole nother tier of that difficulty. If we just add it to the beginning or the end, then it falls under log n. But if it's sorted while we add it in and that stays sorted, then it jumps a tier. I don't quite understand why it jumps a tier, but I remember seeing that.
Seems like it would be n log n because just searching for it would be like a binary search because it's sorted. So you're having it as you're going inside the log. And then inserting would be like what we just talked about above, where it's O of n to insert and shift everything down.
Let me think about this. So definitely something that makes this easier than just sorting the array is that when you're adding n, you know that this letter n is the only unsorted item. You know that the rest of the array is sorted, except for this one guy. So I believe you should be able to find where it belongs with a single binary search. So that should be.
And then, but then inserting it after the binary search would be shifting everything after it down one. So in the worst case,
true.
inserting it near the beginning, you're essentially shifting everything in down one.
Yeah. So that's a really good point. So there's two parts of this problem when we append an item. First, we have to search and find out where the item goes. And then when we insert it, we have to adjust the index of all the other items. So even though, through a little bit of cleverness, we can get the search down to O log n, the insertion is still going to be O of n. And because that's the bigger term than O log n, it kind of dominates it. So we don't really describe it as O of n, or as O log n, we'll just say that's O of n. Cool. And then one more question for you all here. What is the complexity for searching a sorted list? I know we've said this before today. Just if anybody wants to repeat it.
Log in for searching.
That's right. So searching through a sorted list is log n because we can do binary search.
I see what's going on now.
Hey, Raph, I have a comment or a question for
Please.
the previous one.
Mhm.
So even worst case scenario, if we were to add an element to the end of the array and then sort it, the sorting algorithm is still n log n.
Yes, but that's slower than just O of n. So not much slower, but technically O of n is better. I always get mixed up between O of n log n and O of log n, just all the n's and the logs. But yeah, one's better than linear, one's slightly worse. All right, so does anybody notice anything interesting about the relative performance of searching versus adding for the sorted list versus the unsorted list? Anybody?
Is a sorted list more complex? Seems like.
You mean
Like
it's
just
slower?
Sort. Yeah, I think.
Is it always slower?
In some cases it's slower, in some cases it isn't.
And that's why we care about data structures. So yeah, you really said the point here. In some cases it's slower, in some cases it's not. If what we really need to do is search through a list frequently that isn't going to change its size very often, the sorted array is really useful because we only have to deal with the extra complexity of inserting and keeping it sorted when we add new items, which I just said doesn't happen very much for this case. But if people need to access the data very frequently, then binary search helps you do that. So can anyone think of an example, real life, where you might prefer a sorted data structure? Porphy?
Like address book.
Yeah, that's probably my favorite example, honestly, a phone book or an address book. Because people don't get new phone numbers every day. They certainly don't get new phone numbers like every 5 minutes or whatever, which is a time frame that a computer might care about. So you don't really need to optimize for adding new entries to a phone book, but definitely like if I'm trying to, plan out my calendar or like find someone in a hurry, I would really like to be able to search my phone book very quickly. And I would like to not worry about how many people I have in my phone book. I just kind of add everybody who reaches out to me just in case I need to contact them later. And I would hate if that, slowed down my phone book searches just because I added all these LinkedIn recruiters or whatever. So a sorted data structure would make a lot of sense for a phone book because that reflects the trade-offs that I'm willing to make in that situation. Can anyone think of a different situation where I would prefer an unsorted data structure? This might be a little weirder.
I mean, the only real situation I can kind of see that is maybe like for security reasons, like, I don't know, just PII, not really having everything in an organized manner or encrypted.
Okay. So in some ways, having your data unsorted makes it a little bit harder for hackers to work with, but we should trust that hackers can sort data. So if that's the only defense you've got, you're in trouble. I guess one example I could think of, sorry, go on. Did someone have a comment or just forget to mute their mic? All right.
I forgot to mute. Sorry about that.
No worries. So one situation I could think of where you might prefer an unsorted data structure is imagine if you have some kind of like Internet of Things application. So you've got physical devices that maybe have sensors on them and they're sending data to your web application. So like say, for example, you owned a trucking company and you've got like 100 trucks or 1,000 trucks or something. They're driving all over, United States and Canada, and they all have GPS trackers on them that every second they're sending an update to your server about their current location, their speed, and any other diagnostic details, maybe the gas level of the truck. I don't know. So that's going to be a lot of data that's just pouring into my database, like literally every second, just every second from thousands of trucks, every movement they make, the GPS coordinates coming in. But I don't need to read it every second. I don't need like second by second updates on where people are going. It's more just like after the fact, maybe you analyze the data, just make sure, everyone's moving at a good pace. No one's stopping at Wendy's for 2.5 hours or whatever, that kind of stuff. So I would probably prefer an unsorted data structure in that case, because I want to make sure that I can insert data as quickly as possible. And I'm willing to wait a little bit longer in the cases when I want to read the data, because maybe I'm just like running some analysis report overnight and I'll, get it when it's done. So that's probably not a situation you've encountered yet, but I just wanted to get you thinking about these kinds of things. There's always trade-offs when you're designing an application. No data structure is better than another. You just have to consider, what the needs of your application are. All right, so that was the big take-home message. If you remember nothing else today and just like fall asleep at this point, I just hope you remember that different data structures do different operations at different speeds. And so that is a choice that you make as a developer. And actually, I'm going to leave you with an inspirational quote before we go on to the next section. So this is from Linus Torvalds. Does anyone know who Linus Torvalds is?
Creator
Creator of Linux?
Yeah, so he's a creator of Linux, also the creator of Git. So two very important tools we'll be using a lot, authored by Linus Torvalds. He's kind of a notorious arrogant asshole who, he's really mean to other people and people do what he says because he's always right. And so he's got this kind of spicy quote telling who the bad programmers are, who the good programmers are. I didn't understand this for the longest time, but as I'm, maturing as an engineer, I'm starting to appreciate, the different benefits that different data structures give you, and how choosing the wrong data structure can make your algorithms look really ugly, but choosing the right data structures up front can make the rest of your code pretty elegant. So I'm starting to appreciate what this guy has to say about data structures, thinking that maybe he knows what he's talking about. He's been writing some code for a while. So this is a very brief tangent, but I think this is really funny. So sometimes I like to read Ars Technica. It is a tech news website. As a tech news website, they will occasionally publish articles about Linus Torvalds. Here, this is just everything they have tagged with him. Like I said, he's kind of a notorious asshole. So you might notice there is one particular photo of him that they like using for most of their stories about him, just to kind of drive home the point that this guy's an asshole. So I want to say it's like half of the stories about Linus Torvalds on this site are just this one iconic photo of him like flipping off the camera. Apparently in recent years, he's softened up a little bit and he's more like gentle and human and kind and whatever. But for a while, he had that reputation kind of. All right, so now we're going to talk about some actual data structures. So probably the most basic data structure where I want to start in terms of like classic data structures, I'm going to talk about arrays. So first of all, just for clarity, JavaScript has a data structure called arrays. This is not that. So again, just all the names in JavaScript make programming hard to talk about. So we have a thing called arrays, but they're actually a more sophisticated data structure. I'm talking about classic computer science arrays. This is a little bit different. Got a visual here that I think should help you out a little bit. So yeah, so this is kind of a basic article. I don't really care for you to read it, but it has some nice graphics of just boxes and boxes. So I'm just going to show you some pictures of boxes. So in an array, so first think about the memory in your computer, because all of the data that you store has to be stored like in a physical location on your computer in memory. I don't want to get like too into the nitty gritty, like, you know, physical hardware details. You can imagine it as kind of like a grid of slots or a series of buckets, maybe. Like a series of numbered buckets. This is kind of zoomed in more. But so important things to know here is this is supposed to represent something physical on your computer. There's like a memory chip that has all the memory slots like physically arrayed on it. And for an array, that data structure is going to use contiguous memory. So all the data for your array is stored in adjacent slots in memory. So in some ways, this makes arrays very efficient, because if you know where the array starts, and you know that every other member of the array is in adjacent locations in memory, then it's really easy to access items by index. Excuse me. So, you know, if you know the array starts here and you want to access the third item in the array, that's index 0, 1, 2. So you just count ahead 2 spaces. And then that's how your computer can quickly index into an array, because it knows where it starts, and it knows how many spaces ahead to look, and your array takes up contiguous memory. So the downsides of an array are that, so for one thing, you have to declare the size of the array when it's created. So right here, you know, you're looking at 5 items, 5 empty items, but this is still an array. It would take up the same amount of space as if you had actually assigned 5 items to it. So in some ways, arrays are not perfectly efficient, because you have to declare their size up front when you create them. Um, so like arrays will take up the maximum amount of space that they can, even if you haven't filled them up yet. Here's a quick just example of the numbered indices on an array. You know, we've got our different buckets. They have arrays indices starting at 0. That should be familiar to you working with lists. So another complexity of working with arrays, since they have a fixed length, if you append to the end of an array, normally that's pretty fast. You know, if we've only filled in these first 2 items, want to add a 3rd item, that should be pretty fast. But if the array is full, then things get complicated. All right, so here's kind of an illustration of that problem. We're trying to add an E to the start of the array that should push everything forward. The array is already full. So this is a pretty common strategy that your computer might use to deal with that situation, is that if we try to append to an array that's already full, we will create a new array that's twice the size of the original array, copy the original array into the first half of the new array, and then delete the old array. So in that way, you can continue appending items to the array, and the programmer doesn't maybe have to think about that too hard if they didn't do this manually. And the computer is still able to maintain the array in contiguous memory. So this is a pretty slow and kind of expensive process. And it also kind of sucks that you can't predict exactly when this is going to happen, because for the most part, adding to arrays is fast until it isn't. So this is a very basic data structure because it's just adjacent spots in memory, but there are some problems with it, as I've described here. So a different data structure that kind of lets us get around some of these issues. So like, let's say we wanted to be able to add items to our list a little bit more easily, but we didn't actually care as much about accessing the individual items quickly, because again, it's all about trade-offs. There's a different data structure we can use called a linked list. So a linked list is a non-contiguous data structure. Meaning that the elements of a linked list are not necessarily next to each other in memory. So instead, each item of your linked list, each node, is going to occupy one location in memory, and it's going to have a reference to the next node, which could be anywhere else in memory. So, you know, you can't get the whole list all at once just by starting at some starting point and then iterating forward a number of spaces in memory. You have to keep following recursively from next to next to next for each node of your linked list. So there are some downsides, but the fact that you can always add a new item and you don't need to ever resize your original data structure like you do with an array, that is a particular advantage. So I want to just mention real quick, there are a couple kinds of linked lists, 2 basic distinctions. A singly linked list is where each node has a reference to the next node. That is different from a doubly linked list in which each node has a reference to the next node and also the previous node. So a regular linked list, you can start at the head and then traverse that to the end but it's really awkward to traverse backwards. Whereas a doubly linked list, every node has both forward and backwards references. So you can traverse a doubly linked list forwards and backwards. So again, this is a trade-off. The doubly linked list is going to take up more space because it has extra references for the forwards and backwards nodes. But if you need to loop backwards and forwards, then a doubly linked list does that. So depending on your needs, you might choose one over the other. Although honestly, linked lists are not super commonly used on their own. They're often used as part of another data structure. So it's kind of a low-level data structure that's used to build a higher level data structure. So let me go over a couple examples of those. Sorry, so your homework for tonight is really just implementing all these data structures in code. So I do kind of want to show you like how to code up a basic linked list, except that's exactly what your homework assignment is. So I don't want you just copy and paste the lecture notes into your homework tonight. So some things will be left as exercises for the reader, but hopefully from this description of these nodes and the starter code that we provide you on the exercises, you should be able to create a representation of these data structures using, you know, the lists and dictionaries and things you already know about in Python. But so we've got now some subtypes of linked lists, or at least more advanced data structures that can be implemented using a linked list. And some of these you've heard about before, but they're important, so I'll mention them again. The stack. So a stack is like a list, but the only ways we can modify it are with push and pop. So the way we turn a list into a stack is not actually by adding features, by removing them, by providing this guarantee that items from the middle and the start of the list cannot be accessed or modified. We only add and remove from the end. That's creating a stack. I don't want to dive too deep into this because you already heard a lot of great uses for stacks and you've already seen them. You know, they're used for keeping track of the currently executing functions, like in the call stack, which is pretty relevant for us programmers. You can use them to keep track of matching braces as you're opening and closing parentheses and curly braces and brackets and whatnot. So an important way that we describe this is the stack processes items in LIFO order, which is last in, first out. And so that's basically the opposite of a queue. So I'm going to talk about both these together because they're such similar data structures. So a queue is like a list, except you can only modify it I'm actually not sure what the method is in Python for just pushing off the first item. I think you just use pop 0 because pop is more flexible in Python than it is in JavaScript. So I'll just write this in English. Well, so I guess one popular terminology is enqueue for adding an item to a queue. And then you can remove the last item with dequeue. Not like disqualified, but like removed from the queue. So again, this is very similar to a stack. It's a very limited list where there's only one entrance point and one exit point. The only difference here is that the entrance and exit are opposite ends of the list, whereas on the stack, the entrance and exit are the same side of the list. Can anyone think of a use case where you would use a queue?
Maybe like a call center or something where you want to help people in the order in which they arrived in line, sort of.
Yeah, that makes sense. So I don't know if anyone's ever dealt with phone support before, but it feels like the general flow is that there are 10,000 people trying to call in at the same time. And there's like 2 people answering the phones and one of them's out to lunch. So you have to wait. And ideally, they minimize the average wait time for each person. So the first person to get in line is the first person who is met by customer service or whoever. So yeah, I think a queue would make a really good data structure for that kind of a problem. When someone calls in, you add their call or their customer ID to a queue. And then whenever the customer service people are done helping one person, they just take another item off the queue, help the next person. So another example that I thought of, this is a little bit closer to my personal experience. Imagine you're making like a photo sharing website, like kind of like Instagram or something. People upload photos all the time for like no reason, they had lunch or whatever. Every time someone uploads a photo, let's say you need to do a few steps, you convert it to PNG, you downscale the resolution so it's not like 4K or whatever, and then you crop it so that it fits into a square. So for all these tasks that you perform on the photos, you might set up a separate photo editing server. So whenever someone uploads a photo, their photo gets sent to this server in particular, and it processes them one by one. Because it doesn't really matter if they get their photos processed as fast as possible, as long as it happens like, within a few minutes or something. People are usually kind of understanding of taking a few minutes to upload a photo and gets processed on the back end or something. So if you're expecting like dozens of users to be uploading dozens of photos simultaneously, but your backend photo processing server can only handle one at a time, you might put a queue in front of it so that users can freely add their photos to the queue as fast as they want to upload photos. And then the image processing server only removes them from the queue as fast as it's able to process them. But that way nothing gets overwhelmed and your server shouldn't crash, ideally. All right, any questions about stacks and queues? Shouldn't be too crazy. All right, so the last really essential data structure that I want to talk about is the hash table. I'll go a little bit more in depth on this one. Hash tables are a pretty fundamental data structure and they're used in a lot of different situations. So for one just quick example, the dictionary that we use in Python is implemented with a hash table. That's a really good example of a hash table. If you're ever trying to remember like what the heck is a hash table in computer science, just remember how you've used a dictionary. Because it's basically just a list of key value pairs. And then after creating them, you should be able to retrieve a value by the key for that value. So the way we're able to do this is we transform the keys in the table into integers that are used to index into an array using a hashing function. So does anyone know what hashing is? Has anyone heard of this before? Because this is going to be the first part of our hash table implementation.
So isn't it when you do some type of math, kind of like encryption, turn something into something else, and then use a checksum to verify it?
Yes. So we're going to use some kind of math. We're going to turn something into something else. And then at the end of it, it gives us a short string that we can use to verify that, you know, something else is the same. So a hashing, so we're talking about functions, a hashing algorithm. That's a way of processing some input. Hashing function takes some value as input and returns a hash, which in this case today is going to be an integer. Later on in the program, we're going to talk about password hashing, where your hashes are going to be strings, but that's not what we're doing today, so don't worry about that. It's just going to be some value. So also, hashing is a one-way operation. This is different from encryption, which is a two-way operation. Anything you encrypt, you can decrypt. Hashing is a one-way operation. There is no straightforward way to reverse a hash. Kat, question?
Yeah, I was just wondering, is hashing then what, like when websites, you know, if we sign up for a website and we come up with a password, the way that they're stored then in their database, is that like, is it a hashed version of it?
Correct. So yeah, that's what you can look forward to hearing a whole lot more about in the coming weeks. Yeah, I think proper password handling is important. I think a lot of people do it poorly. So I'm happy to tell you my opinions about how it should be done. So another very important feature of hashing, hashing the same input always produces the same output with no randomness. So this is really important because I said before, there's no way that you can reverse a hash. You can't take a hash, then convert that into the original value. But at the very least, because hashing the same value, the same input always produces the same output. If you want to know if a certain value matches some hash, you can just rehash it and then see if the hashes match. So note that it is possible, but unlikely that multiple values will have the same hash. This is known as a hash collision. So a sophisticated real world hash table will have some kind of built-in logic for resolving hash collisions. There are a few different ways that this can be handled, but generally it's a problem and hash tables try to solve it in some way, and better ones will solve it more elegantly than others and have a lower chance of hash collisions. So just to help you visualize this, I'm going to code up a hash table for you really quick. I think this one might be one of the less intuitive ones to get started on. So I'm going to show you a little bit about how the hashing works. So it was not intended to be an OOP lesson, but for implementing these kinds of data structures, I think OOP is just a natural way to approach it. So that's what I'm going to do here. Making a JavaScript class from our hash table. Got to define our constructor function. And there's not going to be anything too fancy going on here. But remember, I might have mentioned that our hash table actually stores its data in an array on our system. We're going to use our hashes to be integer indexes for our array and our system. So we have to keep track of that. So I'm pre-declaring all the space up front, even though my hash table is empty. I'm saying that it's going to take up at most 64 items in my array. And then I need some way to hash values. So this is going to be a little helper function that's going to be used for my other methods for setting and getting values out of this hash table. So this is going to be kind of like an internal sort of private method, not meant to be called outside of the class. So I'm going to start it with an underscore, just an informal convention. It's going to take some key. Now, the way I'm going to compute the hash, this is a little bit dumb. I'm going to be looking at each character individually in the key. It's going to be some string like tomato or whatever. Look at each character individually and then add up the character code for that letter. It's totally arbitrary, doesn't really mean anything, but at least this guarantees that I'll get a different hash for each input, and that different inputs, or that the same input hashed multiple times will give me the same hash. So again, this is not a professional grade hashing algorithm, but this is probably the simplest thing I can show you in JavaScript that technically does the job. Okay, so we're going to loop through every letter in the hash, and they all have a character code. So just for a quick example of that, just open up a JavaScript terminal. So I say hello.char code at 0.
You probably want to go into Python first. Or play my last.
Wait, oh my gosh, yeah, what am I doing? Jesus. I totally know how to code. So yeah, I just opened my terminal. I'm typing in bash here. Bash does not understand JavaScript syntax. I wanted to show you this in Node. Okay, so char code at 0 is 104. Char code at 1 is 101. Let's see, more interesting. So at 2 is 108. 3 is 108 because those are both the letter L in hello, or was it? Yeah. So both L's have the same character code. That makes sense because the same character should have the character code. So all I'm trying to do here is just create some unique, somewhat unique number for this key, for this input string, whatever it might be. Maybe it's hello, maybe it's something else. But at the end of all this, this needs to map to an index in my table. So this is an array with 64 empty spots in it. So you might not have seen this syntax before because usually we create empty arrays. But this is how I can create an empty array with 64 empty spaces in it. So if I want this large number, which, I'm adding 104 plus 101 plus 108 plus 108, but I want it to be within the bounds of 64, just going to use modulus. So mod by the length of the table. So guaranteeing that whatever comes out of our hash function, it's going to be some index of this hash table. So now we've got enough code that I can create an empty hash table. So let's see how we would actually set data in it. So in order to set data in a hash table, just like with dictionaries in Python, you're going to need a key and a value. So the first thing we need to do, because this is a hash table, is we're going to hash the key, and that's going to tell us the index where we want to put the value in our table. So const index equals, so under hash key. So we hash the key, and that tells us where in our array we will put the value, and then we just insert it in there like normal. And so then getting an item, we're going to be given the key, and then we just hash it to get the index, and we retrieve whatever item is at that index. So get key, going to look a little like this. We rehash the key, gives the index, and then we return whatever we find there. So this is the very basics of how a hash table works. It's not very sophisticated because it doesn't handle hash collisions. You know, there's only 64 spots in this array, and there is a reasonable chance that I could hash 2 items that produce the same hash value, because this is not a very smart implementation of a hash table. It's possible in your homework tonight for your implementations, you might find a smarter way to do this that doesn't suffer from hash collisions as catastrophically as mine does. Or maybe you could just Google it, because there are a lot of well-published strategies for dealing with hash collisions. Andrew, question?
Is this what 64-bit and 128-bit encryption is based off of?
I don't want to say yes. I mean, in general, like 64 and 128 is a common number of bits. Like anytime you're working with some number of bits for anything, it's often easiest to have it be a power of 2. I don't know if you played video games growing up, but like the NES was an 8-bit system. Super Nintendo, Genesis were 16-bit systems. PlayStation was a 32-bit system. N64, you can kind of guess what that one was. So yeah, just every generation of consoles when we were growing up, they just double the bits because those are just easy numbers to work with. All right, any other questions about hash tables?
I just have a question about this example specifically, and sorry if you already explained why you did it, but when you created the new array, is there any reason why you chose the length of 64? Or is that just an arbitrary length that you chose?
It was totally arbitrary. I thought it was a
Okay.
nice number just because 64, I think, is a common number of bits, but I could have chosen 12 or 400 or anything.
Okay,
It wasn't
cool.
super deliberate. Yep. Any other questions? All right, so I know that it's 12. There's just a few more things I want to explain to you real quick. I'm not going to code up any lengthy examples, and this is going to be a little bit more advanced, so you're probably not going to be diving into it as much in your homework. But these are just some ideas that I want you to hear about. So if you hear about them again, it's not going to be the first time you've heard it before. So a tree is a pretty common data structure, pretty generic data structure. It's just data structure that has a root node connected to multiple other nodes, which are themselves trees. And then ultimately you'll have a leaf node, which does not have any other nodes connected to it below it. So it's kind of like a metaphor of like a botanical tree, but you have to sort of turn it upside down. So like this is the trunk, and then these are the branches coming up out of it, sort of branching out, literally. So that's a tree. Probably a good example of a tree that you might be familiar with is your file system. The Linux file system is a tree. I go cd/. So this is like the root of my computer. This is one tree that contains all these other folders that are themselves trees that contain the rest of my computer. So more interesting though, note the number of children each node has. This one's got 3, this one has 1, this has 2. Seems kind of disorganized. In a tree, it's not defined necessarily. So more specific than a tree is a binary tree. So a binary tree is like a tree, except every element has at most 2 children. So, 8 has 3 and 10 as its children, 3 has 1 and 6. 10 only has 1 child, so that's fine. You can have fewer than 2 children, but in a binary tree, nothing can have more than 2 children. So binary trees by themselves aren't the most interesting to me, but when we add an additional constraint to them, they can become much more useful. So what you see in this picture, more specifically than being a binary tree, this is a binary search tree. So what that means is that it's a binary tree where at every node, the left child is smaller than the right child. I'm going to write that down. So if you see in this binary tree here, that's how this is behaving. So 8 is our root node. 8 has 2 children, 3 and 10. So the smaller one goes on the left, bigger one goes on the right. 10 only has 1 child, but that child is bigger than 10. So it's the right child. This isn't like an artistic choice that 14 was on the right and not the left. That is like part of the structure of a binary search tree, is that the larger item goes on the right. We see it all the way down here. 6 is bigger than 3, so it goes on the right. But 4 is smaller than 6, 7 is larger, so that's how we split up left and right. So one of the really big benefits of a binary search tree is kind of like the name would imply, is it makes it really easy to do binary search. So remember when we were doing binary search on an array, what made it so fast is that after every iteration, we were cutting it in half and then only looking at half of what we looked at the previous time. And that just kind of happens naturally for us here. Because, first we're looking at the whole binary tree, but if we go to the left tree, we've cut off the entire right subtree. And then again, if I, branch to the right, I cut off this whole left subtree here. So every time you go one step deeper into a binary search tree looking for some value, saying like, no, the target's bigger than the current, no, target is less than the current. Every time you go one step further, you're cutting off half of the nodes in the tree. So this kind of like gives you binary search really easily. Now, note, there are some problems with binary search trees. So depending on, so I'll say, in order for me to search this tree elegantly, it really helps that all of these leaves are of similar length. We're like 3 levels down. If the tree becomes really unbalanced, it gets a little bit harder to work with. So I'm going to just kind of diagram that out for you. This is supposed to be a binary search tree here. Right now, it's just got 1 node. We're starting at 10. So let's say I want to add 11 to my binary search tree. Does that go in the left node or the right node?
Right now.
Right.
Okay, so I'm adding 11 to my binary search tree. That goes in the right node. Gonna put that over there. Okay, great. So now let's say I'm going to add 12 to my binary search tree. Where does this go?
Right.
Okay. Okay, so here's the real tricky one. What if I want to add 13 to my binary search tree? I'm just kidding. This isn't any harder. Yeah, it's still going to the right. Okay, so this illustrates kind of an interesting feature of binary search trees. Does this actually look like a different data structure maybe that we might be familiar with?
It looks like an array.
So I think I heard the correct answer. This is just a linked list. So In the best case scenario, binary search trees are very efficient. So let's actually go back to our cheat sheet over here. We got data structure, binary search tree. So average case is very good. It's O log n for everything, which, I mean, it's never a constant time, but it's also always better than linear for the average case. So that's pretty cool. Not every data structure can do that. But in the worst case, it's O of n, which, so you'll notice the worst case for binary search tree is as bad or worse than a singly linked list. Because the worst case for a binary search tree is that it just is a linked list. So it couldn't possibly do better than a linked list. I think that's kind of funny. I don't know. To the extent that data structures are funny, this makes me chuckle. Okay, so that's a binary search tree. More sophisticated implementations of a binary search tree will have an auto balancing feature, is what it's called. So just like when we added an item to our sorted list, we had to make sure we put it in the right spot. More sophisticated binary search trees will make sure that you can't just add an item anywhere, but after you add an item, it'll search through itself and rebalance itself so that it doesn't just all go in one direction like this, but it's reorganized in a way so that binary search actually helps you cut it in half multiple times. Okay, and then one last data structure that I'm gonna share with you, and then we can be done for today, is the B tree. So this is fairly advanced. I'm not an expert in this, definitely too advanced for us to get into in this program. But the reason why I wanted to mention it is because I think the name is really confusing. It sounds like something you already know, but it's not. So if someone asks you in an interview, do you know how B trees work? The answer should be no, but I would love to learn, because this is not a binary tree. I don't know what the B stands for, but it's not binary. So what a B tree actually is, it's similar to a binary search tree, except instead of every node having exactly 2 children, it can have n number of children. So this looks like a 5th order B tree, meaning every node has 5 items. You can see, this is a 5-element array with a child, it's a 5-element array. All of its children are 5-element arrays. So this is a B tree. I believe that this is the actual data structure that is used in most contemporary databases. So like, I know a lot of the stuff we've been teaching you is kind of like abstract and academic, and you're probably not going to like actually touch it. Like, you're not going to actually need to implement a doubly linked list for any professional problems. It's like an interview question and kind of your foundational computer science knowledge. But like, if you want to get deep into databases, like if you become a web app developer and you decide that databases are your favorite part of the whole stack, there's a very good chance that you will need to become well acquainted with this data structure. So yeah, I just wanted to clear up the confusion because it sounds like something you already know, and I just didn't want to risk you, sounding ignorant in an interview or whatever. Yeah, so let me just make a quick note about that. A B tree is not a binary tree. It's similar, but can have more than 2 children per node, depending on the order of the tree. So for example, 4th order tree has at most 4 children per node. There are more rules to it. That's the basics of the B tree. They're commonly used in popular databases. So I guess also if anyone ever asks you, like, what do you know about databases under the hood? You could say, I think the tables are implemented with B trees, and then somebody might give you a nod. All right, so sorry for going over. That is actually all the content I've got for you today. Let's open it up for questions, and then we can take lunch. Jake?
Yeah, so I was wondering, are we gonna have to perform like memory management operations and stuff like that, like allocate and deallocate things and like, free up memory and stuff like that? Does JavaScript or Python make you do that on your own, or do they have like all kinds of built-in things that handle that for you?
So JavaScript certainly does not do that, does not let you do that. Python, to my knowledge, does not let you do that, but also Python has a handful of advanced features that let you kind of, dig under the hood and do things that maybe you shouldn't. So Python might have that functionality. I'm not 100% sure, but it's certainly not common. Most commonly, like most modern programming languages are garbage collected is what they call it. That is just periodically as your computer is running and processing your program, it'll just check all the variables that are defined and all the data that it's allocated memory for and whatnot, and ask itself like, is the code still able to access all these variables? Because like if there is some data that just cannot be accessed by any part of your code, like there's no function that refers to it, it's not assigned to a variable, it's not in an array anywhere, then your computer will safely assume that you meant to delete this data, and so it'll just delete it for you. I'd say in decades past, a lot of the bugs that happened in programs were just for people not managing their memory correctly. They take too much memory for an array and they don't release it when they're done with the array, or other similar subtle bugs. I don't know, it used to be a lot easier to write bugs. I'm very glad that we get to work with garbage collected languages. So in theory, it's a little bit less efficient because you don't ever get to say like, hey, I'm done with that variable, get it out of the memory. But I think it's definitely a good trade-off. Actually, Ankur, so you've written C++ a whole bunch. Do you have any comments on the topic of memory management?
It's not very fun. So I think, yeah, a lot of languages kind of do have garbage collection, more modern languages, C and C++. You kind of got to manage yourself and you get into a lot of trouble if you mismanage memory in your application. So it's kind of a more advanced topic, but we don't need to worry about it because Python, JavaScript kind of do the hard work for us behind the scenes. So we should be thankful for that.
Cool. Do you know if there's any way to manually access memory in Python?
I do not know if that's possible.
Okay. I don't know if it's possible, but if it is, I'm not going to do it. So I was just curious. Cool. Any other questions from folks? No questions, going once, going twice. All right. Thank you everybody for attending my data structures lecture. Really loved all your questions, all the engaged activity here. So today is Thursday. It's going to be a pair programming day. I'm going to Slack out your pairs sometime before we all get back from lunch. Please comment on the Slack message if you got the same pair as last time, because if too many people got the same pairs, I'll just regenerate a list. If only one person is a repeat, then maybe talk with a group of 3 or try to just interject yourself somewhere. Or if the pairs don't work for whatever other reason, feel free to Slack me. And yeah, you got a bunch of exercises for this afternoon, just implementing in code all the data structures that I talked about. So I hope you can convert those, prose pseudocode ideas into actual code. Yeah, that's all. Anything else? Last minute questions? Nothing? All right.